To round off this first week of the course, what I'd like to do is to give a bit of context and talk about some other ways that you can build functional programming languages. Haskell embodies a certain set of design choices, and I think they're good choices, but what I'd like to do is just give you a bit of context by describing Haskell and three other languages and comparing what they support. So these are languages you may come across in the future, you may have heard about already, but it's useful to know how Haskell sits in the landscape, as it were. So we can ask certain questions when we're designing a functional programming language. One thing we can think about is how evaluation takes place, because remember that's at the heart of how a functional programming language works. We write expressions and those expressions are evaluated to values. One way of doing it is, as in most traditional languages, the way you evaluate a function applied to its arguments is that you first evaluate the arguments and then you apply the function body to those values. So arguments first, then function body. That's something we're familiar with. But it's possible that you don't need to evaluate all those arguments, or if those arguments are complicated structures, you don't need to evaluate all of those structures in order for computation to continue. And that approach, you could call it an approach by need or a lazy approach, is the approach that there is in Haskell. And that enables a certain style of programming that we'll talk about later on in the course. So Haskell does have this distinctive lazy approach to evaluation. A second question is what happens with side effects, things like printing out or having mutable variables that change their value as computation goes on. Are those allowed in a language or not? Or if not, is there some way that you can do some sort of mutable programming, some sort of impure programming inside a pure context? And that's something, again, that Haskell is quite strict on, but we'll see that other languages behave differently on this. And we've seen already that Haskell enforces what's called strong typing. You can tell whether a program is going to produce a type error without running that program. Now, not all languages do that, and there are advantages to that. You can write code that applies to all sorts of different values without worrying about what type those values have. But you have the downside that any errors you have, any type errors you get, will be postponed until runtime rather than catching them early. And I think it's a truism, but I think it's no less true for that the earlier you catch errors, the better, and the cheaper in terms of development. So there is a downside to being in a weakly typed language that you discover type errors late. And then finally, and this is perhaps a quite different kind of distinction, are the programs in the language themselves data? And that's not at all how Haskell looks at the world, but this is something that some languages do. They're reflexive. They allow you to look at every program as being data. And so anything that you produce is something that you could potentially execute. Okay, now let me try and give you an idea of the range of what can happen by looking at four languages. We look at Haskell, but also at OCaml, Erlang and LISP. And we'll talk about their different choices for these design decisions, and then talk about what they represent in terms of usable languages, what they get used for. So let's draw this table, just categorizing them in terms of these four criteria. So we know Haskell is lazy. It does evaluation by need. We've not talked about that really yet in detail, but that's something I will talk about later. It's pure. Nothing in Haskell has a side effect. Full stop. It's strongly typed and it's not reflexive. So it's quite controlled. You know what type any expression will be, and you are sure that that expression won't have side effects. That's in contrast to OCaml, which is strict, so that follows the normal the more usual approach to evaluation, that you evaluate function arguments first and then only then apply the body of the function to those values. It's impure. It contains mutable variables. It allows you to do all sorts of side effects as a part of expression evaluation, but it is strongly typed. So type errors are caught early, but it does relax the restriction on side effects. Again, it's not reflexive. Erlang is also strict. Erlang's a different language in that it's functional, but at its heart is concurrency. So while Erlang doesn't contain variables, mutable variables that can be updated, it does allow concurrent things like spawning a new concurrent process to occur as a side effect of evaluation, or it allows a message to be sent. So that's why I put impure in parentheses there. It's somewhat impure. It's impure in certain directions, and it's weakly typed. Type errors are delayed until runtime with Erlang, and again, it's not reflexive. Now, the final language on the list, and the oldest in this whole selection, is Lisp. It's a language for symbolic processing. It is strict, it's impure, it has side effects, it's untyped, and yes, it's reflexive. So programs are data. So you can write, as a result of a program, you can write another program. And so it provides this symbolic, reflexive programming model, which is quite different from the value-oriented programming of languages like Haskell, OCaml, and Erlang. So looking at these four languages, Haskell, as we've said, is pure, but it does allow effects to come in, side effects, as what are called, we can model them by what are monads and other types in the language. And what monads do effectively is allow us to write programs that, when we run them, will be side effecting, and then we run those. But once we run a program, we're no longer in the world of pure Haskell. So we have these two levels, if you like, we have the pure world of Haskell, and then it's possible to take parts of that and run them as programs that affect the real world. But we'll talk a lot more about that towards the end of the course. And one thing in having strong typing, it allows us to do type-directed programming, type-driven programming in an effective and safe way. And similarly, OCaml allows us to do that. And OCaml is used heavily for example, by Jane Street to build the whole of their infrastructure on which they're a very successful financial trading company. And they drive a lot of the open source development around OCaml. So it's entirely possible to do serious programming in a strongly typed but impure language. And indeed, Erlang shows that it's entirely possible to write substantial systems like all the infrastructure that WhatsApp has, and all the telecoms infrastructure or a lot of the telecoms infrastructure that Ericsson built, in a language which is functional at base, so not allowing side effects in terms of updatable variables, but allowing very high intensity concurrency to be built on top of a functional substrate, as it were. And Erlang also has an interesting design decision in terms of failure handling. It models failure handling through what's called a fail early ethos. If it looks like something is going wrong, the program itself doesn't try and recover. What it does is fail and use a separate part of the system, what's called a supervisor, to recover from that. And that modularization of failure has been a huge success in the Erlang world. And then finally, Lisp. Really, it's a symbolic processing model rather than a functional model. As programs are data, you can't type them, but Lisp is used very heavily in certain areas, and large Y Combinator came out of a startup which was Lisp based, for example. So all these languages get used in practice, and it just shows the wide variety of things that come under the heading of functional programming. But in the rest of this course, we'll be concentrating on Haskell, which is lazy, so evaluation is by need, it's strongly typed, and it's pure.